So here we are in Bumthang Valley. We have come to make few programs in the Ong Di Choling Lower Secondary School, and Mr. Martin Thorn would be telling us about what air pressure means. So let us now see and find out what exactly are we talking about when we think of air pressure. And I am now pumping up a ball. This ball was too flat for us to play football with, so I'm pumping it up. And what I've done is I've put more air into it. So I've taken the air from the atmosphere and I've pushed it through a small area and I've filled the ball with it. And the reason I can do this is because the air is a gas. The air is compressible. We can squeeze a gas. Quite different from a liquid. It's harder to squeeze a liquid. And as you know, it's not much fun trying to squeeze a solid. So these three bottles show us the three states that matter appears to us: solid, liquid, and gas. And today's program, we're going to be focusing especially on the gas that surrounds us, the gas that we breathe from the atmosphere. Okay, so the solid, as something that is not compressible, like this stone, has very little energy. Its particles are very tightly compressed together to make it a solid. Now we move to the liquids. So the liquid, as the water here in the stream, is flowing. It's moving freely. But it will stay within the stream bed because of gravity. So you can see that compared with the stone, compared with a solid, liquids have more energy. Their particles are more spaced apart than in a solid, and that means that they are less dense. And now the gases. Lots of room. They move everywhere. As you can see from the tree above us, the gas that makes up our atmosphere is moving freely. There's a lot of energy, the particles have a lot of space, and it's the least dense of the three states of matter. The most dense being the solids, less dense than a solid is the liquids, and then lots of freedom, lots of energy, and very little density, the gases, such as the atmosphere. And that's what we're going to be talking about today, the atmosphere. So you probably know we use kilograms or kg to measure mass. These carrots weigh half a kilogram. But does the air around us, does the atmosphere also have mass? I've brought something and we can do a little experiment to test this. So let's try this. We have two empty balloons, and as you can see, when the wind stops, they're balanced. Now I'm going to take the one balloon . And I'm going to add air to it. Now, if air has mass, we can see there's more air in one side than there is on the other. So let's see what happens. You can see when I hold it still that indeed the full balloon has considerably more mass than the balloon without any air. So we've proven with this experiment that air indeed does have mass. Here we are at Yotong La, the highest point between Trongsa and us here in the Bumtang Valley. And the barometer has not shown a difference, but I am really noticing it. My ears are popping. You see, we are perfectly designed to live at sea level. Everything is in balance. When we move up from sea level to high altitudes, the air pressure changes, and that causes two main problems for us. The first problem is that there is thinner air where there is less air pressure. So high in the mountains, it's more difficult for us to breathe. The other reason is changing altitude can be difficult on our bodies. Popping of ears, bleeding, pain, sometimes. Now, when we were down in the valley, we actually had more air to breathe. Air, what is it? It's a gas. It's a mixture. We often talk about the oxygen, and that's actually what we use. It's the only part of the air we're using. Most of air is nitrogen, and the nitrogen we find in the atmosphere can't really be used by living things. So what we're looking for is the 21%, and that is the oxygen. Now, when we're at the top of a high mountain, because there's less air pressure, the air is thinner, and there's less oxygen. It's the same percentage of oxygen, the same ratio of oxygen to nitrogen, but there's less of it. And for this reason, mountain climbers, when they go high above 5,000, 8,000 meters, need a bottle of oxygen often in order to feed their blood and their bodies. So the air pressure on the inside of the body wants to be the same as the air pressure on the outside. And when we move from a low altitude area of high pressure to a high altitude area of low pressure, that's the natural thing that our body does. These chips and corn snacks were packaged much closer to sea level, where the air pressure was high. When they arrived in Bhutan, they were in a place that had much lower air pressure. So the inside was different from the outside. What happened? Well, the bags expanded because there was less pushing them down than there was inside. If we kept on going and traveled up to higher altitudes, it's possible that these two bags would actually burst and make a mess all over the place. Another example is a drinking straw. When we're drinking out of a juice box, what we're actually doing is changing the pressure on the inside. And then the pressure on the outside will push the juice into our mouth. So, as this is almost at the end, what's happening here is that the air pressure is pushing in on this. All I'm doing is removing the air from the inside. All I've done is reduce the air pressure. It's the surrounding atmospheric pressure that has actually crushed the box. And the only reason we're not crushed by it is it's always equalizing. When we move up, we blow our noses, we blow the ears, and it equalizes the pressure. So the inside is the same, which helps objects usually keep their shape. We know that air pressure or atmospheric pressure affects our bodies and many of the things we do. And we've discovered that it also changes some of the rules. Now, water behaves in a certain way at sea level. If we take a thermometer used to measure temperature, what we expect at sea level is that water is going to freeze, will become ice at 0 degrees Celsius, and at 100 degrees Celsius, it will become water vapor. So it goes from solid to liquid at 0 degrees, and then from liquid to a gas at 100 degrees. But what happens if we change the atmospheric pressure? So here we are at Bumtang, 3,200 meters above sea level. Now the rule is, water at sea level boils at 100 degrees. Can you predict what it's going to be doing at 3,200 meters? And we'll just wait for it to boil. Now that we have our water boiling, we'll check the temperature. And it is boiling at, instead of 100 degrees, as it would be at sea level, at 1 full atmosphere of pressure, we're down to it boiling at 91 degrees. So we're here at 3,200 meters above sea level, and the air pressure, the atmospheric pressure, is less, and so the water will boil earlier. Now that sounds like a good thing, but for cooking it can cause problems because there isn't enough energy in the water for it to do the job that we want it to do. So we need to find out a way that we can add more energy to this water. If we keep the water cooking here, it won't get any hotter than 91 degrees because of the atmospheric pressure. All it will do is continue to boil and evaporate and turn all the water into vapor, water vapor. So how can we add energy to water that is already boiling at 91 degrees so that it does its proper job of cooking? Well, the solution to this problem is air pressure. A clever invention, the pressure cooker. What the pressure cooker will do is keep the water inside. It's got a top on this to prevent the water from escaping as steam. And because it's a fully sealed lid, it won't allow anything out, and we will increase the pressure inside the pot. This pot is at the atmospheric pressure that will have water boil at 91 degrees. We can add energy by enclosing that and increasing the pressure. And by increasing the pressure, we are adding energy and we are able to cook the dal or the datse or whatever it is that we're making. A clever way to overcome the problem of cooking at high altitude. So with all this atmosphere weighing us down, all this air pressure surrounding us, we're going to want to measure it. And for that, we have an instrument called a barometer. This measures air pressure. This is called an aneroid barometer, and it's quite a clever little thing. As the air pressure pushes down on a metallic strip, you can see the needle moving. So the needle will change as the air pressure changes. And from these changes, we can find out which parts have low pressure, which parts have high pressure, and where high pressure and low pressure come together, that's when the things get exciting in the air. Clouds come, rain comes, weather patterns are created by differences in air pressure. Even more accurate than aneroid barometer would be something that isn't used much anymore, a mercury barometer. What's great about a mercury barometer is it's so simple. So to show how a mercury barometer works, we need to understand that air pressure does a wonderful thing. When there's air pressure in this tube, the same on both sides, then the liquid will remain at the same level. So pressure likes an equilibrium. Pressure likes to be even, both sides. It will even itself out naturally. But if we increase the pressure, that will change the level. Well, similarly, what we have here is a column, a tube full of mercury. And the air pressure surrounding it will push the mercury when the air pressure increases or ease off on the mercury. And as a result, the mercury will go up or down with the changing air pressure, indicating changes in the weather patterns. So here we are at Chamkar Meteorological Station with Ugan Dorji, our meteorologist, to show us what they're using now.
This is our latest technology, installed 2010, and these are the parameters. This one is solar radiation. We have a wind direction installed up to 10 meter height, and this one is max humidity and temperature sensor, and these are the transmitter. This record transmit to our headquarters, and these are the parameter.
So this is where the barometer is.
Yes.
So the reading here was 744 hectopascals. If we were at sea level and we had the same weather conditions, that would be over 1,000 hectopascals. So we're in a whole new realm when we move up to a high altitude like this. So, Ugan Dorji, when we look around at the weather today, what can we see about the air pressure and what it's doing?
Actually, air pressure increased when the high temperatures forecast.
So when there's a lot of pressure, it's keeping the clouds away.
Yes.
And when there's low pressure, it draws the clouds in, and low pressure will bring us rain.
And hailstorm.
So at the moment, we have a fairly high pressure here, but down the end of the valley, there's quite a bit of low pressure. That was a low pressure system, bringing in the wind. Okay. So what about this pressure that surrounds us? How strong is it? Well, as we were saying, if the inside pressure is the same as the outside pressure, it's not a problem. My hand looks like this. It's happy. It's in no pain. The inside pressure is the same as the outside air pressure. The atmospheric pressure is equalized inside and outside of my body. Instead of my hand, we're going to use a water bottle. And I have hot boiling water here, and just going to heat up the air on the inside of the water bottle. Make it nice and hot. So we're increasing the energy on the inside of the bottle, nice and hot. And I'll take the water out so we only have hot air, and then we'll close the bottle quickly and see what happens when it cools. Now what is pressing on the bottle? It's the same air pressure that's on the outside of my hand. But unlike my hand, the inside pressure of the bottle is much less. We've had hot water and hot air inside the bottle, and now that hot air is cooling down, and as it cools down it loses energy and it loses density. Welcome to Curje. We've brought you here to show you another type of atmosphere. So far in the program, we've been talking about the atmosphere of air that surrounds us. This atmosphere is liquid, not gas. And as a liquid, it's much denser than air, the gas. So the particles, the small pieces, the small bits that make up water, are much more densely packed than the particles that make up air. And that's why we say that water is more dense than air. And I'm going to show you that when you go down into the atmosphere of water, something similar happens in the change in atmospheric pressure. If you look behind me, you'll see there is white in the water. Now this is the gas, air, mixing with the liquid, water. But for the most part, once you're below the water, the thing you notice most is there really isn't much gas, there isn't any oxygen. So if we were at sea level, we would be surrounded by 1 atmosphere of pressure. And I've brought you down to the river here to show you that it doesn't stop there. The atmosphere is everything surrounding us. So when we are in the water, the atmosphere is no longer air, but is now water. So I've created, with aluminium foil, a bit of a pocket. I'm going to put my hand in the water. If we were at sea level, I would have 1 atmosphere of pressure around me, and that's made up of air. When I go into the water, the pressure increases the farther I go down into the water. And you can see when I bring it back up that the imprint of my hand has been made by the depth of the water. And that's because the atmosphere in the water increases the farther I go down. So when divers swim below the surface, they have to keep this in mind. Every 10 meters below the surface is another atmosphere of pressure. So we start above the water at 1 atmosphere of pressure. 10 meters below the water, we are at 2 atmospheres of pressure. 20 meters below the water, we're at 3 atmospheres of pressure, and so on. So you can imagine that divers have to be very careful of this, the people swimming under the water. Now we've talked about the mass of air forming the atmosphere that is above us and weighs down. So we're talking about something that is 11 kilometers, 11,000 meters thick, up to maybe 100 or 150 kilometers thick. It's what makes the Earth different from every one of our planets. None of the other planets has an atmosphere that will support life the way Earth does. But this atmosphere weighs us down. So, if you can imagine us on the Earth, standing there, watching our football match, and on top of us is this mass of air. But the mass of air isn't only 1 or 2 kilometers thick. It's very, very heavy. It's massive. So what happens at sea level is we have lots and lots of air pressure pushing us down. So, how's your hand? Let's go up. Let's go up a short mountain. Same mass of air, but he's moved up. Let's go to the top of Jomolari. So you can see there's not much air pressure at the top. Where the air pressure is down at sea level. And the higher the elevation, the less the air pressure that's weighing us down. At the bottom of that column is going to be denser than the air that is here, because there's pressure on the air, as well as the air putting pressure on all of us when we're at sea level. So it's just like a stack of books. The closer you are to sea level, the denser the air. The closer you are to sea level, the more the atmospheric pressure, the greater the air pressure. And as you move up in the atmosphere, the air pressure gets less and less and less, and the air surrounding you becomes less dense. Today's program has been about air pressure. We've looked at the 3 states of matter, solid, liquid, and gas, and their different densities. We've proven that air has mass, and how the higher we climb, the less is that mass of air weighing us down. We've seen how the body and other objects respond to changes in atmospheric pressure, and how these changes affect such things as high-altitude cooking. We've ventured down into the liquid atmosphere of water and then come up again to marvel at our planet's atmosphere, that thick layer of air and air pressure that supports life on our planet Earth.
Until next time, thank you for watching tutorial, and if you have any comments or suggestions, please write to us again. Our address is tutorial@bbs.bt.